So today's lesson is going to be on solving trigonometric equations with identities. So we're going to use the identities that we covered, all of those ones that are on the formula sheet, to solve a trigonometric equation. So some sort of an equation, something with an equal sign that contains trigonometric functions. Let's get going. So like I said, today's plan is we're going to look at how to use trigonometric identities to solve equations that contain more than one type of trigonometric ratio. So you'll look at some today that might have sine and cos or sine and tan, basically two or more different types of trig ratios inside of a single equation. It's just going to be a full gauntlet of problems in today's lesson. We technically we technically are just using skills we previously developed. We're not really covering anything new today. That being said, in this video, I'm going to do something that might be a little annoying. Every time we have a single trig ratio to solve. So for example, if I say we have like cosine theta equals 1/2, each time we get down to a single trig ratio to solve, I'm going to remind you to pause the video and think about it, or at least solve it, just so you get that experience going in here. We are going to need to know how to do this a lot. So whether you use your special triangles or you use your calculator, we need to make sure we practice this today. It seems annoying, it seems small, but believe me, it's better than just sitting and watching me solve all these problems. Another thing, this is some good news, maybe a little bit of motivation. This is the last concept of chapter 6, and thus of our entire trigonometric unit. That's awesome, right? Trigonometry is finally over here. We're doing really good. Anyway, let's move on. Not going to waste your time. So far we've been concerned with using trigonometric identities to either simplify a long trigonometric expression or to prove a new trigonometric identity. Today, we'll focus on solving trigonometric equations for particular values of x within a specified domain. These equations will often contain more than one type of trigonometric ratio. When solving trigonometric equations, you generally will want to have the entire thing, this is super important, the entire thing in terms of one type of trigonometric ratio. That's where the trigonometric identities we've studied come into play. So if there's anything you need to get out of this today is whenever you have a trigonometric equation, you need to get the entire thing in terms of one type of trig ratio. So you look at your formula sheet and you basically look at all your identities and think, how could I basically use any of these identities to change what I was given into just one type of trig ratio? Let me show you a bunch of examples. Here we go. So first example, straight out the gates, algebraically solve the following equation over the domain x is between 0 and 2 pi. So we know we're dealing with radians here today. And state answers as an exact value. So that means no rounding using a decimal. We have to have exact value answers here with pi, right? So what we've got is 2 cos squared x minus 3 sine x equals 0. Now, the issue with this is we have two different types of trigonometric expressions here. That doesn't really work too well when you're solving trig equations. When you are solving a trig equation, so something with an equal sign in it, it's got a bunch of trig equations in there, or trig functions in there, I should say. When you're solving a trig equation, you want to get the whole thing in terms of one type of trig ratio. So if you take a look at your formula sheet right now, what I want you to think about is how could I replace either cosine squared x or sine x so that it's in terms of the other one here. So in other words, how could I turn this thing into into sine, and how could I turn this thing into cosine? Now, here's a bit of a tip. We've studied a ton of different identities. We've studied the Pythagorean ones, we've studied double angle ones, we've studied sum and difference and all that. But one of the types, of course, the Pythagorean, as I could say, identity, they involve things that are like cosine squared or sine squared, those kind of things, right? That might be your hint that this is the one we want to get rid of. We might want to get rid of this cosine squared. Notice that one of the identities with cosine squared in it is the one that says sine squared theta plus cosine squared theta equals 1. Now, what I've told you before about trigonometric identities is that any of the ones that are given on your formula sheet, you are more than free to rearrange them however you wish to get whatever you want all by itself. If we could get cosine squared all by itself in this identity, we could just use whatever that's equal to and substitute back in. Well, in this identity, if we just subtracted sine squared theta on both sides, you would see that we would have cosine squared theta equals 1 minus sine squared theta. What that basically means is I can replace this cos squared x with 1 minus sine squared x. At least that way, this entire trigonometric equation will just be in terms of sine. Let's give it a shot. So I'm going to replace this cosine squared x with what I got over here. This is going to be 2 times 1 minus sine squared x, and then minus 3 sine x equals 0. Now, of course, this is looking pretty messy, so why don't I just take this 2 and double dip it through? That's going to give me 2 minus 2 sine squared x minus 3 sine x equals 0. Now, hopefully what you notice here is this is kind of like a quadratic equation involving sine, right? There's a sine squared, and there's just a sine, and then there's a number all by itself. How about I move all of this over to the other side so I can write this in order from highest degree power to lowest degree power, and so that I can have a positive leading coefficient on my sine squared, because this is right now, this is minus 2 sine squared, right? Anyway, if I add this all over, put it onto the right side, I'm going to have 0 equals positive 2 sine squared x plus 3 sine x, because I moved the minus 3 sine x by adding it over to the other side. And then I have to subtract the 2 from the other side here to get it over. So minus 2 on the very end there. Now that I have it written like this looks a lot more like just a standard kind of quadratic. And we could factor this to help solve the equation, because when you have a quadratic, you need to factor it in order to find where it's going to be equal to 0. It's going to be the exact same kind of idea here. So to factor this, it kind of looks like an adapted sum product rule question. The reason I say that is, we notice we have 2 of our squared thing, and then 3 of just the normal one, and then minus 2 in the very end. Whenever you have a leading coefficient that isn't 1, you usually have to use your adapted sum product rule. So the adapted sum product rule says you're going to solve this by looking for 2 numbers with a sum of the middle number, which is 3, and a product of the first number times the last number. So 2 times minus 2, that'd be minus 4. So 2 numbers, you got to think, 2 numbers with a sum of 3, but a product of negative 4. I think that would be positive 4 and minus 1. So positive 4 and minus 1 would solve this. So I'll split apart my middle term. First term's still going to stay the same here, but split apart the middle term using positive 4 and minus 1. So plus 4 sine x, and then minus 1 sine x minus 2. So notice that I just kind of split apart that 3 sine x there. We didn't have to change anything. Then you put brackets around the first 2, brackets on the second 2. This is just, old adapted sum product rule. Hopefully that makes sense. If it doesn't, you'll have to ask me for help on that. But anyway, notice how when I put brackets around the second 2, though, because there was a minus in between, I got to change this to a plus. That's because the minus would otherwise double dip its way through there, and we want to prevent that from, making that into a positive. So we make it into a positive so that when it double dips through, we're back to our minus 2 that we would hope for. Anyway, long story short, let's factor out what we can. I think we can take out a 2 sine out of the first couple bits here. So this will be 2 sine x, and then we're going to be left with just sine x plus, I guess if we divide this by 2 sine x, we're just left with 2 minus, there's nothing we really can take out of this. So you always just take out 1. So minus 1, and that leaves us with sine x plus 2. Now the good news is we have sine x plus 2 here, and we have sine x plus 2 here. In other words, they're matching. That tells us that we've done this correctly. So our factored form is going to be 0 equals sine x plus 2 times 2 sine x. Oops, not 2x, sorry, 2 sine x minus 1. So again, just this duplicate factor multiplied by this minus this, right? It's just the adapted sum product rule. Again, if you're struggling with that, make sure you come ask. I can show you some more simple examples to get the point across. Anyway, long story short here, what we have is we have 0 equals this times this. The only way that that's going to be true is if either this piece was 0 or if this piece was 0. Well, if the first piece there was equal to 0, like the sine x plus 2, if that was equal to 0, sine x plus 2, if that was equal to 0, then we would say we have sine x equals negative 2. Well, hopefully you know by this point, sine actually has a range of negative 1 to positive 1. So there's no way that sine x is going to equal negative 2. It's just not going to happen. And if you don't believe me, you could always try taking inverse sine of this. You're just going to get an error. So this one is actually impossible. That'll never equal 0. As for the other one there, though, 2 sine x minus 1 equals 0. You could add 1 on both sides and then divide by 2. That's going to give us sine x equals 1 over 2. Now, you might remember the beginning of the video, I kind of warned you. I said, hey, we're going to get to points where you have to solve individual trig expressions. Yeah, this is going to be one of them, right? So I want you to pause the video here and think about what values of x within this domain, and notice it's radians, would solve this mini equation right here. So pause the video, give that a try. So there's a couple different ways you could do this. 1/2, of course, is part of a special triangle. So if you're really keen with special triangles, you could get it that way. If you didn't get it that way, my advice is honestly just to kind of cheese this. If you turn your calculator to degree mode and then take the inverse sign of positive 1/2, that'll tell you your reference angle. And it'll actually spit out 30 degrees. Now, we don't want to be dealing with degrees. So right after you get that, immediately turn it right to radians. 30 degrees in radians is pi/6, right? Now, from our cast rule, which tells us where things are positive versus negative, since we have a positive sign, we're either in this quadrant or this quadrant. Pi/6 is in this quadrant, so this right here, this pi/6 is going to be one of our answers. However, you need to realize that sine is also positive in this quadrant right over here. The answers to trigonometric expressions do not just exist in one quadrant unless explicitly stated. You have to consider the cast rule when solving them. So we could also be in this quadrant 2 here. The good news is, though, our reference angle is still going to hold still. Use a reference angle of 30 degrees to come up from this angle right here. That would give us just 30 degrees below 180, which is 150 degrees. But we want in radians, so of course it's just pi/6 underneath pi. Well, imagine pi is 6 pi/6. Take 1 pi/6 away from that. We have 5 pi/6 as being our other answer. Whew. So there's a lot to this. We used an identity first and foremost. We solved it using quadratic stuff. So we used like the adapted sum product rule. And then, as if that wasn't hard enough, we had to use our understanding of chapter 4 concepts, where we had to be able to solve just a mini little trigonometric equation like sine x equals 1/2. What I'm getting at is there's a lot of background information in this this final topic here, like a lot. So if you're struggling with this, make sure you make note of what steps you're struggling on and coming and reaching out and asking for me for any extra help. Anyway, let's try another question. This one's quite similar to this first one here. Here we go. Oh, sorry, I was totally forgetting. We need to verify this in our graphing calculator. So your graphing calculator can actually help you out with this as well. I want you to plug in this original thing here into y1. Now, just by the way, to put this into y1, like cos squared x, if you haven't done this before, you're going to have to say 2 cos, and then it asks you for x right away. So you have to just put that in there and then square the outside. As long as you have brackets around the x in this, your calculator knows that if you put a square on the outside, it's not applying to the x, it's applying to the cosine. Kind of a little bit of a weird thing, but if that's how you put it in your calculator, you're golden. So again, just graph that in your calculator, set your window to this and make sure you're in radian mode. And the question is, do the graphical solutions match the algebraic solutions you found? Give you a second just to pause the video here and graph that. And hopefully you graphed it. I'll draw you what I kind of had here. I think my Y window was just -10 to +10. So what I saw on my window looked something like this. So this is my window. So my window looked something like this. Again, this is my x-axis here. It looked kind of like this. Yoink, and then up, and then it kind of like did a wavy thing kind of here, and then that was about it. Now, judging from where my points are on my grid, like it was something like that, and keep in mind our scale here is pi/2. This point here, I really didn't draw this very well. It was more like way back here. This point here, I could actually assume it's pi/6. This point over here, I could actually assume to be 5 pi/6. And if I wasn't 100% certain, I could always find my my zeros as it is. So if you go second trace and then select where it says 0, you could actually prove that that's what those points are. The algebraic solutions are a lot more important than this. I'm not going to do another graph one today. I don't really think it's worth the effort. Anyway, moving on. So this question, this is very much like that first one we did. We'll go through this one a little quicker. If you want to pause the video and give this one a try, you can. You don't have to by any means, but you can if you want to. But otherwise, I'm going to go over this one. So just like before, we want to get this in terms of 1 trig ratio. Immediately, since I see this squared, that tells me that's probably going to be the one I want to get rid of. Matter of fact, this is the exact same kind of thing as what we dealt with before. So I'm going to change this right away to 3 minus 3 sine x minus 2, and then I'm going to replace cos squared x with 1 minus sine squared x. And this, of course, equals 0. Now, this 2 needs to double dip its way through here, but notice there's a negative attached to it. That has to follow through as well. So what I'm going to have is I'm going to have 3 minus 3 sine x, 2 times 1 here, it's going to be minus 2, and then minus 2 times minus sine squared x. is going to give me plus 2 sine squared x, and that equals 0. Since we now have a positive leading coefficient on our highest degree term, I'm not going to move things over to the right-hand side here. I think it's going to be just fine on the left side where it is. So this is going to give me 2 sine squared x. I'm just rearranging this now, just by the way, minus 3 sine x. And then 3 minus 2 is plus 1 equals 0. So now I have that written in descending order of degree, like I usually like seeing it. Once again, this is an adapted sum product rule question. We're looking for two numbers with a sum of the middle term. So the sum is going to be -3, and the product is of the first term times the last term. So 2 times 1 is just 2. So think hard about this one. What are two numbers with a sum of -3, but a product of +2? Well, that'd be -2 and -1. So I'm going to split this middle thing apart using -2 and -1. So I've got 2 sine squared x minus 2 sine x minus 1 sine x. So there's my -2 and my -1. Plus 1 equals 0. Put brackets around the first two, brackets around the second two. Because there was a minus here, it needs to chase its way through here. It's not going to change the first one, though. It's just going to change the second one. So instead of +1, I have to switch that to a -1 because this negative would double dip through and change it back to a +1. That's all we're doing there. Now I got a factor out of the first two here. I could take out a 2 sine x, which is going to leave me with a 1 sine x minus 1. Out of these two, the only thing I could take out is a 1. So I've got -1 times sine x minus 1. Notice we have sine x minus 1 and sine x minus 1. That matches. That tells us we've done this correctly. So I've got sine x minus 1 times 2 sine x minus 1 equals 0. So just like before, we have to solve for where each of these pieces is equal to 0. I'm just going to do this over here. So sine x minus 1 equals 0 when, if we just rearrange this, when sine x equals 1. Now, sine x equals 1, that means if you think about on a unit circle, sine represents our y value. So our y value, where our y value is 1, that would be at an angle of 90 degrees. But again, we're dealing with radians. So I guess I have to say that x is equal to, in radians, pi over 2. So that right there, that's going to be my answer for that one. And there's not a duplicate answer to that. There's only one place where y is 1. It's just up there, right? It's not like where's y 0.5? Well, it could be there. Could also be there, right? That's why the cast rule works, right? Because sine, cast, sine is your y value. Y values are positive up here. Anyway, I'm ranting. The other one is this 2 sine x minus 1. 2 sine x minus 1 equals 0. Add 1 divided by 2. We have sine x equals 1/2. And that's just like the one we saw on the other slide. Actually, it's the same thing I just put here. I wasn't even thinking. Holy smokes. So where is sine x equal to 1/2? So in other words, where's your y value equal to 1/2 on the unit circle? Well, that would be where x is 30 degrees and where x is 150 degrees. But again, radians, just like before, it's where x equals pi over 6 and where x equals 5 pi over 6. Because again, we use our reference angle of pi over 6 in this quadrant to come away from pi. And that's it. That's all there is for that one, right? So that one was a lot quicker than that first one we did. Hopefully the concept is going okay. Anyway, we've got a bunch more we got to do here. It's going to probably be a pretty long lesson today. I apologize, but it is what it is. All right, next one. Algebraically solve the following equation over this domain. Hey, this is nice. This is in degrees, and it's just a normal domain. That's probably better. This, however, not so nice. We got sine squared, we got tan, we got cosine. We got 3 different trig ratios going on here. This is like the Neapolitan ice cream of trig equations here. We got 3 different flavors. What the heck, right? Anyway, what I would first do is we need to try to figure out some way that we can get this all in terms of 1 trig ratio. Now, given the other ones, you might be tempted to say, oh, there's a sine squared. Maybe I should change that over. I wouldn't get too crazy with that quite yet. What I would do, to be honest, is I would get rid of tan first. Generally speaking, sine and cosine, those are pretty happy. We don't mind those ones. Sine and cosine are pretty good, generally speaking. Tan, however, is weird, as would all 3 of those weird reciprocal ones, right? Sine and cosine, though, we like keeping those as much as possible. So what I'll do first is I'll see if I can get rid of tan x. Tan x actually has a pretty nice identity to it. If you check on your formula sheet, it's actually kind of right in the top right-hand corner. Tan x is just sine over cos. Let's start there, see where we go, right? So we have sine squared x equals 1/2, and then instead of tan, I'm going to write that as sine x over cos x, and then times by cos x. Now, if you're pretty keen, you might notice what's going to happen here. Sine x over cos x times cos x. Well, that cos x on the bottom and this cos x right here, those are actually going to cancel each other out, because this is multiplying this. You can think of cos x as cos x over 1. That's just going to knock that bottom denominator there totally out. So what we're left with is we're going to be left with sine squared x equals 1/2 sine x. Now it's just in terms of sine. We didn't even have to touch the sine squared. Look at us go. Awesome. That was pretty lucky. Now to solve this, because we do have a sine squared, to be fair, that's like a quadratic. When you solve a quadratic, everything has to be on one side. So I think I'm going to minus the 1/2 sine x over. This is going to give me sine squared x minus 1/2 sine x equals 0. Now you might be tempted to say, oh, well, we got to do our sum product rule stuff. You don't actually have to, because we don't have a constant over here. We could just pull out a sine x. So if I pull out a sine x here, I've got sine x on the outside. If I take sine x out of this, I have another sine x. Minus, if I take sine x out of this, I just have 1/2. So long story short, either this piece equals 0, which means we have sine x equals 0, or this piece equals 0, which means we'd have sine x equal to positive 1/2. Well, sine x equals positive 1/2. We're getting sick and tired of solving that one. We've solved that one several times here. This time around, though, we are dealing with degrees rather than radians. Sine x equals 1/2. Again, that's just going to be x equals 30 degrees and x equals 150 degrees. So using 30 degrees as a reference angle from 180, right? As for sine x equals 0, that's one I'm going to want you to pause the video here and think about. Well, hopefully what you thought about is the fact that sine x represents your y value on a unit circle. Well, where's the y value equal to 0? That'd be over here, and that would be over here. So we're going to have two answers for sine x equals 0. So for sine x equals 0, we're going to have x equals 0 degrees, because that would be over here, and x equals 180 degrees, which of course would be over there. Now, for the previous example, find the general solutions for x as an element of R. These are always annoying, but they're not as bad as a lot of people make them out to be. Basically, look for some sort of a pattern. If we go back to the 4 solutions we had, that was just within our first 360 degrees. Look for any patterns, right? These two are consistently going to be 180 degrees apart. So there's a pattern. These two, however, not really so much of a pattern there. You might say, oh, it's 120 degrees apart. But if you go 120 degrees above this, you're at 270, which is something totally different. It's not even related to these ones at all. So we can't use the difference between those ones to make a pattern. Long story short, if we're going to make a general solution, or general solutions, we should say, we could say x equals, we'll do the 0 and 181. You could say 0 plus or minus 180. I will write that actually. 0 plus or minus 180n, where n is an element. N is an element of the integers, but this 0 is not really doing anything. So you could just say, honestly, 180n, where n is an element of the integers. If you want the 0 plus or minus, that's fine. I would never dock marks for that, but it is what it is. That just takes care of these two. That's all that just did. These two, on the other hand, I think we're just going to have to treat them separately. So I'm going to go like this. X equals 30 degrees plus or minus 360n. So a full circle times n, where n is an element of the integers. And then the last one would be x equals 150 degrees plus or minus 360n, where n, once again, is an element of the integers. So all we did with that is we're just basically saying, what are all the possible different answers that we could have within a full domain? So it doesn't even matter if it's just within like one circle. We're talking all the circles. The whole x is an element of real numbers, the whole thing. Anyway, moving on. Next one, algebraically solve cosine 2x equals cos x. Give general solutions. Oh, geez, that's fun. Give general solutions expressed in radians as exact values. Oh, this one's just a thriller, isn't it? Holy smokes. All right, so here's my hint to you. We still want to keep everything in terms of 1 trig ratio. And you might say, hey, look, this one already is in terms of 1 trig ratio. But there's a problem. We have cosine 2x. Double angle identities are our absolute worst nightmare. We almost never, ever want them. They're always terrible. We always want to get rid of them with very, very few exceptions, like really, really few exceptions, right? Anyway, what I'm getting at with that is, if you look on your formula sheet, you can see a bunch of different formulas for cosine 2x. Let's pick the one that keeps just cosines. Cosine 2x, according to your formula sheet, could also equal 2 cos squared x minus 1. So how about I replace that right away? This becomes 2 cos squared x minus 1 equals our cosine x, right? So I just replaced my double angle identity with this guy right here. Now everything's in terms of cosine. This is a pretty clear quadratic kind of cosine question here. So let's bring the other cosine over to the other side. This is going to give me 2 cosine squared x minus cosine x minus 1 equals 0. Once again, this is an adapted sum product rule question. We're looking for two numbers with a sum of your middle number, so a sum of -1, and a product of your first number times your last number, so a product of -2. Pretty sure that would be -2 and +1. So if it's -2 and +1, we can split apart our middle term. We can say this is 2 cos squared x minus 2 cos x plus 1 cos x minus 1 equals 0, and then put brackets around the first two and brackets around the last two. Now, I'm going to take out what I can from each of these. Out of the first two here, I could take out a 2 cosine x. So 2 cosine x times what's left over, which is just cosine x minus 1. Plus, out of these two, the only thing I could take out, once again, is just a 1. So 1 times cosine x minus 1 equals 0. And hopefully you see the cosine x minus 1. They match on both of these. So we've got cosine x minus 1 times 2 cosine x plus 1. So 2 cos x plus 1 equals 0. Oh, okay. Anyway, this is pretty tiresome. There's quite a long question here. Anyway, if we're going to solve this now, just basically say where each of these brackets are equal to 0. So for this one, we would have cosine x equals +1. And then for this one, we would have cosine x equals -1/2. These ones are going to be a little tricky. So I'm going to ask right now, you don't have to worry about the general solution quite yet, but I'm just going to ask, what would be our solutions in degree or in radians, sorry, for this one and for this one? Pause the video, see if you can figure that one out. Okay, before I actually write it out, I'm actually going to show you here. Just draw a unit circle. Also mention your cast rule. That was a terrible circle. It's not even centered at all. By our cast rule, we know cosine is going to be positive in these two quadrants and negative like it is here in these other two quadrants. Now, cosine on a unit circle spits out your x value. So cosine x equals 1 is another way of saying, like, what is your x value where x is 1, right? So where x is 1, that would just be at 0 degrees, or in other words, 0 radians, right? So from there, we'll just go over here. We can say that x is going to equal 0 radians. That's going to be for sure our only solution for that first piece. That's it, right? Now, as for cos x equals -1/2, you have some options. If you're pretty keen with your special triangles, you might actually know what angle that is right off the top of your head, which is pretty impressive. But if you're not, you could always use your graphing calculator using inverse trig. And remember, you just never use inverse trig of a negative number, so you'll have to use inverse cos of 1/2. I would also do it in degrees and then turn it over to radians. It's just easy that way. Long story short, you're going to get a reference angle, I'll call it XR, a reference angle of 60 degrees, or in other words, pi/3. That's just our reference angle because I would have taken inverse cosine of +1/2. Since this is our reference angle, and since cosine is negative, we know we're either in the S quadrant or the T quadrant. The S quadrant is going to require us to come down from pi, like go smaller than pi, which is actually up on the unit circle, but it is what it is, right? Smaller than pi, or we're going to go bigger than pi. And the amount we're going to go smaller or bigger by is pi/3. Long story short, we're going to have x equals, if we go smaller than pi by pi/3, 2 pi/3. Because think of pi as being 3 pi/3. You just take 1 pi/3 away from it. And then likewise, we would have 4 pi/3 if we went 1 pi/3 bigger than it. Now, there actually is a really brilliant pattern here. If you don't see the pattern, it's not the end of the world. Your general solution literally can just be plus 2 pi n, where n is an element of the integers, for literally each and every single one of these. There's nothing wrong with that at all. That is totally correct. However, I have noticed that each of these, even including 0, each of these are 2 pi over 3 apart from one another. And if we went another 2 pi over 3 ahead of this one, we'd have 6 pi over 3, which is just the same thing as 2 pi, which is actually the same angle as 0. So guess what? If we want to be super crafty here, and if you don't notice this, it's not the end of the world. Don't panic. But the most crafty possible general solution, and therefore, in my opinion, the best general solution would be something like x equals 2 pi over 3 n, where n is an element of the integers. What that just means is n could be any number. We're just doing multiples of 2 pi over 3 times n. And n, because it's an integer, it could also equal 0, right? So if n was equal to 0, we'd be catching that one as well. That's a brilliant answer. That would be a really smart way of doing this. But again, this is just fine as well. Either of these work just fine by me. Just keep in mind on a diploma exam, this might be like a good multiple choice kind of question they might give. That would be the better answer, or that'd be the answer that would appear in your multiple choice section, right? So just be mindful that you can shrink something big like this down into something a little smaller. Okay, I think we've only got one more question here. Yep, we do. One more question. We're going to make it. Here we go. One last question. We got this. So once again, algebraically solve this. And unfortunately, once again, it wants general solutions. Just a total pain here. So first things first, we notice we have two different kinds of trig ratios here. We got cosine x and we have secant x. Secant is a reciprocal ratio. We really don't like those. We don't like double angles even more, but we don't like reciprocal ones either. Let's change this reciprocal ratio over to what it actually is. Remember, secant is 1 over cosine. So this is 5 times 1 over cosine. Here's what we've got. We've got 3 cos x plus 2 equals 5 over cosine x. Because again, that's 5 times 1 over cosine. So why not just write it as 5 over cosine x? Now, what I would do next, to be honest, you might be tempted just to subtract this fraction over to the other side. That would be fine. But this fraction is really going to make things tough to solve. So what I would do personally is I would just multiply everything here by cosine x, right? If I multiply everything by cosine x, we're going to have 3 cosine squared x plus 2 cosine x equals 5. And from there, I can just minus 5 from both sides, and I have 3 cosine squared x plus 2 cosine x minus 5 equals 0. That's just a pretty normal quadratic, right? So we're going to look using, once again, adapted sum product rule. We're going to look for two numbers with a sum of the middle number, so a sum of 2, and a product of 3 times minus 5, which is negative 15. Let me fix that, negative 15. There we go. So think about that one for a second. What is two numbers with a sum of 2, but a product of negative 15? I think that would be 5 and negative 3. So I'm going to write the negative 3 first, just so I don't have to use that weird bracket rule again. So I'll say 3 cosine squared x minus 3 cos x. So there's my negative 3 plus 5 cosine x minus 5 equals 0. Put brackets around the first two, brackets around the second two. I don't need to worry about changing the sign here because there was a positive in the middle. Then ask yourself, what could I take out of these first two? Well, it looks like I could take out a 3 cosine x. So I'll do that. 3 cosine x. This is going to leave me with a cosine x minus 1 plus, what could I take out of these two? It looks like I could take out a 5. So I'll say plus 5 times cosine x minus 1 equals 0. What do you notice? As I always say, these two things match. So why don't I just say we have cosine x minus 1 times 3 cosine x plus 5, and that all equals 0. So long story short, either this piece is equal to 0 or this piece is equal to 0. If the left piece is equal to 0, we have cosine x equals 1. If the right side is equal to 0, we'd have to minus 5 and then divide by 3. We'd have cosine x equals negative 5 divided by 3. Or in other words, that's cosine x equals negative 1.6 repeated. Hopefully you remember, cosine, just like sine, has to always be between negative 1 and positive 1. So this is good news for us. Cosine x equals negative 1.666. That's never going to happen. That's a number less than negative 1. Never going to happen. If you don't believe me, you could always use inverse cosine on that. Ha ha ha. That does not work. So the only thing we have here is cosine x equals 1. And we did that one just a second ago, so I won't even get you to pause the video here unless you really, really want to. Cosine x equals 1. Think of your unit circle and think of the fact that cosine spits out your x value. Where is x equal to 1? Right there. So in other words, it's going to be x equals 0. That right there is our solution. However, it wants general solutions in radians. Well, this could be 0. It could also be a full circle, so 2 pi. It could be 2 full circles, so it could be 4 pi, yada, yada, yada. What's the pattern? We're just multiplying by 2 pi each time. We're just increasing by 2 pi. So the pattern here, my general solution would be x equals, you could say 0 plus or minus 2 pi n, where n is an element of the integers, or you could just forget the 0 altogether, because in all honesty, 2 pi times n, 0 is included in that n there. It is what it is. Boom, there's our answer. Whew, that was quite a long video. I mean, we've had longer, but holy smokes, as you would notice, this kind of concept requires so many different layers of information. You need to know basically how to use your identities. You need to know how to factor a quadratic, even using the adapted sum product rule, and even when it's using trig, right? Like you can pretend cosine squared, for instance, is an x squared, but it is what it is, right? And if that wasn't enough, you also need to know how to solve individual trig ratios like this one. There's a lot of stuff you got to know here. If you are struggling, please make sure you let me know. I can help you one-to-one, right? Promise. Anyway, for practice, there's some practice questions. Now it says tomorrow's quiz in 2022. It's not going to be the next day. It's going to be the day after. But the upcoming quiz, we can say, will contain 5 written response questions, 1 diploma question, and blah, blah, blah. You can read the rest. Anyway, without further ado, if you need any extra help, please make sure you reach out.